We're going to accelerate quickly from the universe of 2 dimensions to the universe of 3 and show you some of the ways things get more interesting. And this will encapsulate some of the content and types of things that you will be thinking about through a good portion of the first week of class here. So first of all, I've drawn a 3-dimensional coordinate system here. Calc 1 and Calc 2, you just have the good old-fashioned XY plane, which has now been tipped over into the page, and the Z-axis can now spring to life, going up vertically. When you're reading books or notes that other people have created, pay close attention to how the axes are oriented, because some people make this positive X, positive Y, positive Z, or might even have X and Z and Y. So the axes can come in different configurations. I like to pretend that the XY plane used to just be the page, and then we went poke, and it tipped over into the page and landed the way I've showed you. And then the Z-axis, like I said, springs up from the middle. The easiest object to graph in 2 dimensions is a line, right? So 2x plus y equals 4. When we move to 3 dimensions, unfortunately, that is no longer a line. And here's why. It's still a line in 2 dimensions, so I'm actually going to plot this. Let's see, in the xy plane, I can figure out where that line goes pretty quickly just by finding the intercepts. When y is 0, I would have 2x equals 4, or x equals 2, and so the x-intercept right there, when y is 0, is that point. And when x is 0, then y is 4, like so. And now this in the xy plane, here's that line. It's kind of a negative slope, and if we didn't have the z-axis, that would have been the end of the story. Okay? Now, we're in 3 dimensions, though, which means that z can take on different values. The line we've just drawn is in the xy plane, which is z is 0. So let's say we go up to z equals 1, and we're going to look out away from the z-axis and discover what points we see that want to be on this particular thing, 2x plus y equals 4. Well, since z isn't in the equation, the fact that we're sitting on z equals 1 makes no difference to the points that we're collecting. We just need to go out and say, okay, fine, we're now at z equals 1. We still need to go out and, for those points that have a z-coordinate of 1, find all the points that satisfy 2x plus y equals 4. And that's going to be the same line we just drew, except elevated up to z equals 1. Like so. And if we went up to z equals 3, then we would need to go find all these points that satisfy 2x plus y equals 4, except that have a z-coordinate of 3. And so what's happening is, as we go up, the shape that we're finding is not changing because the z-coordinate is not influencing the recipe that we're following to collect all the points. So remember that the equation of a thing just tells you what all the points on the thing have in common. And so we're finding here where all the points that had 2x plus y equal to 4 when z was 0, 2x plus y equals 4 when z was 1, up here 2x plus y equals 4 except when z is 3. We could even go in the other direction. We could go down to say z equals negative 1 and so on. And hopefully what you're seeing is the formation of a plane. And this one happens to be vertical. So in 2 dimensions, this is a line. In 3 dimensions, this is a plane. Okay, but we're still after that equation of a line in 3 dimensions. So surely all we have to do is go and put in a z-coordinate, right? And now we'll have a equation of a line in 3 dimensions. Well, not so fast. This isn't a line either. This is yet another plane. It's just a plane that doesn't happen to be vertical. So let's go to this particular item and do the same thing. Hey, let's set z to 0. Well, at z equals 0, we're in the xy plane. What should we see? Well, we should see 2x plus y equals 4. Well, remember, that was this. And I'm going to use this same picture because some of those points are already there. Okay. What if we set y equal to 0? And we set x equal to 0. When x and y are both 0, that means we're moving up and down the z-axis, right? And to be in this club, the club of 2x plus y plus z equals 4, if x and y are both 0, we had better come up with z equals 4. So I'm going to borrow my pen back. So that point wants to be on this surface. This point does too, this point does too. We already knew about those. And I'm going to leap a little bit here, but what I've done is provided enough information to draw what this thing looks like. This is another plane. The rates of change of coordinate in the z direction, the y direction, the x direction are constants. That's what makes a line a line. In 2 dimensions, it's what makes a plane in 3 dimensions. Just like we need 2 points to draw a line, we need 3 points to draw a plane. And for this surface, we have 3 points. Those 3 points determine the plane. So now, I'm going to try my artistic skills. Here is the intersection of that plane with the 3-dimensional coordinate system. That's not I haven't drawn the whole thing, but imagine the infinite plane that I've now shaded red a little bit of. It's now tilted and it's going into the page. That is what this looks like. So, what the heck do we do to get a line in 3 dimensions? Well, that's tricky, sort of. To do a line in 3 dimensions, we need to bust out parametric equations. Until later in the semester when we will learn to use vectors to describe lines, and that's actually a little bit more efficient, and it will turn out that using vectors to describe lines versus using parametric equations turns out to be the same thing in the end anyway. But for now, I'll just leave it with this. You know from Calc 2 what parametric equations look like. They're little bitty equations that depend on some parameter. In this case, it will be the parameter t. And the parameter t is the thing that generates the rest of the coordinates. So to get a line in 3 dimensions, we have to have a set of 3 linear parametric equations in which the parameter t, which is allowed to run from -infinity to infinity, the parameter t generates each of the x and y and z coordinates. So let's make up an example like that. How about 1 plus 2t for x, 0 plus t for y, and -2 minus t for z. When t is 0, you see we'll get the point 1, 0, -2. Well, that is up here at the point 1, 0, -2. So there is 1 point on the line. When t is 1, we're going to get the point, I did t equals 0 in my head, that was easy, right? T equals 1, we're going to get the point 3, 1, -3. Then if I go up here, let's see, x equals 3, y equals 1, and then drop down to -1, 2, 3 in the z direction. And now we have 2 points which we can play connect the dots. And there is our line in 3 dimensions. Now it's really hard to see exactly which way it's going because my artistry is horrible, and we're trying to draw 3 dimensions on a 2-dimensional piece of paper, and you kind of lose things a little bit, you lose detail. But this is the big difference now. As we escalate from 2 dimensions to 3 dimensions, it's not necessarily going to be as simple as just, oh, this was a line before, so when we throw in z, we're going to have a line again. That's not how it works. For now, you want to recognize something like this as a plane, and you want to recognize that to construct a line in 3 dimensions, for now, we're going to need parametric equations. They're not complicated, but we still need them.